People began first talking seriously about software as an engineering discipline, about software engineering, in 1968 in Garmisch, Germany, at the first NATO Software Engineering Conference. And this conference was prompted by what people at the time called the software crisis. Computers were getting bigger and faster, and programs were getting bigger and more ambitious, and it became clear that we really didn't have much of a clue about how to reliably build good software quickly or predictably. And so there was a crisis, and NATO, of all people, decided to call a conference and start talking about software engineering. It's almost 50 years later, and this is when you're probably expecting me to say everything's the same, nothing's changed. But actually it's changed a lot. I think we're a lot better at building software. We've gotten a lot better, especially over the past 20 years or so. Dan North this morning talked eloquently about some of the improvements that have been made in the area of process, and certainly certain kinds of software we've gotten fairly good at building. But I don't think you can credit the field that we call software engineering, the academic research field of software engineering, with much of that improvement. And looking back on these 50 years, it seems clear to me that the software crisis was actually just phase one of a longer software engineering crisis. And over the years, this crisis is characterized by a series of different problems. The first one that prompted the Garmisch conference was, well, clearly we need it, but we don't have anything. So let's figure out what we can do and what we can add to our processes and methods to do this more reliably. And the second phase, which started in the mid-70s and extended kind of into the mid-90s, was characterized by, well, we have something, but it doesn't seem to work very well. And it was during this period in the 80s at university in Texas that I was taught classical software engineering methods, and I was a little skeptical of them even then, but thought I'd give them a try. And then in the early 90s, I was working in Perth for 3 years and worked for a company that was seriously trying to do a better job at serving its clients and building good software. And so they continued my education in those classical software engineering methods and confirmed my hunch that they didn't work very well. The third phase really started about 1995, and I describe it as, well, screw engineering, we have to have something that works. And this was when agile methods started to gain prominence and have some discipline around other ways of doing things. But then lately, I would characterize the fourth phase of the software engineering crisis this way. A large number of people in our industry are voicing the opinion that engineering and software are incompatible, that software development is not engineering, will never be engineering. Engineering is an inappropriate metaphor for software development, and we should just forget about that and consider ourselves a craft or an art or a science or any number of other things. You can see this in, a few years ago, Tom DeMarco, who played an important role in early days of software engineering, wrote this article, Software Engineering, an Idea Whose Time Has Come and Gone. Earlier this year, I captured a representative tweet. Let's stop calling programmers engineers. It's factually wrong and insulting to both professions. Same goes for software architects. And Ryan Bergman is not special in voicing that opinion. I've seen a lot of people say similar things. And just a few weeks ago in The Atlantic, there was this article, Programmers, Stop Calling Yourselves Engineers. The tagline down there says, it undermines a long tradition of designing and building infrastructure in the public interest. And that tagline betrays a bias in the way that writer is thinking about engineering that we'll come back to later, and I think that leads him astray. But anyway, this fourth phase of the software engineering crisis that, software and engineering just aren't compatible, to my mind represents a genuine crisis. In our field, we design and build useful things for people. Failure of those things causes loss. If the failure of the effort to build the things, if the effort to build the things fails, it causes loss of opportunity and money to the organization that is driving that development. If the software itself fails once it's been produced, the loss can range from, user inconvenience and happiness, which might seem like nothing, but it's really not, all the way through monetary losses of various kinds and even life and limb. That means, to my mind, by definition, our field is doing engineering, albeit at this stage of our maturity with a small e. It requires the care and responsibility that has been traditionally associated with engineering disciplines and rigor and practices. We've tried to replace that in our field with notions of craftsmanship, and that's good, because good engineering, I think, brings along with it a sense of craftsmanship and care about the work that you're doing. But if you believe, as I do, that we should be seeking ever better ways to reliably build quality systems, then I think you should be alarmed that many in our industry are turning their back on engineering as a model we should aspire to. So if we want to look at how to fix this and how we should view software development as an engineering discipline, we kind of have to look at what went wrong. And the problem seems to be here at step 2. Because if that had worked, then there would never have been a step 3. And that was the focus, that those methods of software engineering didn't work in the experience of the people who tried them. And that's what led people to conclude that, we had something and it called itself software engineering, and it didn't work. So maybe engineering is just not right for us. But I want to draw your attention to this word, something. We had something that called itself software engineering, but that was just one view, one possibility of what software engineering could look like, and I think it's the wrong view. Now, you should be feeling skeptical right about now, because I'm just this guy that you've probably never heard of, and I'm telling you that all those great minds that worked for 20 or 30 years to try to craft this field and set of methods and practices called software engineering got it dead wrong. But consider the ridiculousness of the situation at that point. We had a field where, with a set of practices and methods that were called engineering, and everybody in the field knew that those practices didn't work. And that's ridiculous, because in every other field that aspires to the title of engineering, the term engineering is reserved for practices that work. You're not allowed to call it engineering unless it works reliably. That's the whole point. And that's not what we had, so that was the wrong path. And our biggest problem now is that we've never really faced up to that and admitted it to ourselves that that was the wrong situation. So that's what we're going to do for the rest of the talk. We're going to look at how traditional software engineering went wrong, look at where that left us in the in the 70s, 80s, and 90s, and then try to think about what real effective software engineering would look like. So how we got here. Unfortunately, we got here because the people who started this effort, starting in 1968 and 69 and then moving on, misunderstood two crucial things: software and engineering. Now you should really be skeptical. But look, it's easy to see how they misunderstood software. Think about what things were like back then. Computers in the 1970s were painfully constrained and by today's standards almost comically diverse in terms of hardware and operating systems and APIs and things like that. The programming languages that were in use then lacked expressive power. And in short, a lot of things that we just don't really spend much time caring about that are virtually free to us were very, very costly then, and that kind of led them to focus on these immediate problems that they had and treat it as the fundamental problems of software development, and they turned out to be kind of transient. In his keynote, Adrian mentions that change in cost model about how at one point we were trying to optimize for machine cycles and memory and things like that, but now the most expensive thing is programmer effort, and our optimization strategies need to change. It takes a little more to understand how they misunderstood engineering and ended up aiming at the wrong goal. Put yourself in the place of the people who are trying to get started on forming a software engineering discipline. We're a little bit different from the existing engineering disciplines. We don't work with physical materials and forces very much. We're not constrained by the physical world nearly as much as they are. So it's natural to expect software engineering in its details, the particular practices and methods, to be a bit different from traditional engineering disciplines. But we should start looking at maybe what the philosophical essence and core of engineering is, because we're going to want to share that. But then they ran into a problem. And the problem is that it's hard to find a definition of engineering outside of the realm of a particular kind of engineering. And it turns out that engineers just don't seem to like writing about engineering very much. They'd rather just get on with it and do some. I found a quote from a mechanical engineering professor at the University of Texas writing about this kind of thing. Unlike the extensive analysis of the scientific method, little significant research to date has sought the philosophical foundations of engineering. Library shelves groan under the weight of books by the most scholarly, most respected people analyzing the human activity called science. No equivalent body of research treats the engineering method. That's Billy Von Cohen. He's a mechanical engineering professor at UT. And he's right. In several years of looking, these are all the books that I have discovered that really address what engineering is at its essence, independent of a particular discipline or set of practices. And you'll notice that none of them were available at the time of the first NATO Software Engineering Conference. So, failing to find any guidance like that, I'm oversimplifying and being unkind, but it seems to me that they basically looked around at the most visible and prominent and easy to understand kind of engineering around and decided to base software engineering on civil engineering, which, if you learn about these things, it's the oldest, most well-established, best understood branch of engineering, and it's the one that's inherently least like software development. But it seems like a silly situation, but the software engineering literature is full of assumptions that are drawn on an analogy with civil engineering. So I'm going to look at a bunch of flawed or misleading assumptions that you see all over the software engineering literature that kind of led us astray. The first one is engineering is defined and predictable. The best example of this I've found is a fairly recent quote from about 6 years ago by Bruce Eckel in an article where he was essentially arguing that software development isn't compatible with engineering. And he wrote this: programming is not some kind of engineering, and you can almost hear the sneer in his voice, when he says that word, when he writes that word. It's not some kind of engineering where all we have to do is put something in one end and turn the crank. How many of you in this room have a traditional engineering education outside of software? So, shout me down if I'm wrong about this next slide, but there is no kind of engineering where all you have to do is put something in one end and turn the crank. Engineering is, by its nature, a creative effort trying to build and design something new. And it's full of false starts and dead ends and experimentation. Now, granted, there are some little areas of engineering disciplines where it is a well-understood problem. Freeway overpasses, you measure how long the span has to be and how high it has to be, and the characteristics of the soil on either side, and you can kind of pull something out of a book and just apply that. But in general, even civil engineering still involves a lot of creation and exploration of the design space. To quote Billy Von Cohen again, the engineering method is the use of heuristics to cause the best change in a poorly understood or uncertain situation within the available resources. Does that sound familiar to you as software developers? That sounds like what we do. But that's a mechanical engineering professor describing what engineering is to him. One way to kind of see what's going on here, chemical engineers don't design fixed structures, they design processes. And so as a part of their work, they have developed the notion of process control models. And it's a spectrum. It goes from defined on one end to empirical on the other end. And I'm going to use quotes from Schwaber and Beadle's original book on Scrum, because they based some of their work on Scrum on this idea. The defined process control model requires that every piece of work be completely understood. A defined process can be started and allowed to run until completion with the same results every time. On the other hand, the empirical process control model provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. Now, chemical engineers use this model to describe the product of chemical engineering, but it can also be used to understand the process of engineering. And which of those defined or empirical processes does software development sound like? It sounds like the empirical one. And in his paper, A Rational Design Process, by David Parnas, one of the towering figures of software engineering, wrote, "The picture of a software designer deriving his design in a rational way from a statement of requirements is quite unrealistic. No system has ever been developed in that way, and probably none ever will." That sort of points out that the empirical process model is what is appropriate for software development. And in fact, if you look at engineering disciplines across the whole variety of them, you will see that they kind of lay out all across this spectrum. Sure, civil engineering is much closer to the defined end of the spectrum for several different reasons, but software development is not the only one that's more toward the empirical side of things. So, second flawed assumption. Engineering is applied science. This is a widely held opinion, and there's a software engineering researcher at the Software Engineering Institute named Mary Shaw, and she's very sharp and has done a lot of great work. But this slide from one of her presentations really makes me laugh. Some new thing starts off being produced as a craft, a little cottage industry, and but then production techniques are added and it becomes a commercial endeavor, but it doesn't really get serious until you add science, and then it becomes professional engineering. This is a good time for you to learn about the term parasitic credibility while I take a drink. I love this quote from aeronautical engineer J.D. North to the Royal Aeronautical Society in 1923. "Aeroplanes are not designed by science, but by art, in spite of some pretense and humbug to the contrary. There is a big gap between scientific research and the engineering product, which has to be bridged by the art of the engineer." More recently, Henry Petrosky, who has written more and more eloquently about engineering of all kinds than anybody else I know, he's a mechanical engineering professor at Duke University, wrote this. He's a structural engineering professor. Throughout history, a full scientific understanding has been neither necessary nor sufficient for great technological advances. The era of the steam engine notably was well into its second century before a fully formed science of thermodynamics had been developed. Indeed, sometimes science has impeded progress. Had Marconi believed his physicist contemporaries, he would have known that wireless telegraphy signals could not be sent across the ocean around Earth's curvature. Engineering is both more and less than applied science. Another flawed assumption, requirements can be understood in advance. This is mostly true for some kinds of engineering disciplines, but not true at all for others. Software is not the only discipline in which requirements are discovered through a process of trial experience and feedback. In his book, What Engineers Know and How They Know It, aeronautical or aerospace engineer Walter Vincenti writes, engineers frequently have to make decisions of great practical consequence in the face of incomplete and uncertain knowledge. Does that sound familiar? That sounds like software development too. Flawed assumption number 4, engineers design via documents. And this is actually true, but it's been misinterpreted in misleading ways for software development. In a talk at UPSLA 2000 something or another in Montreal, I heard David Parnas say this, in engineering, people design through documentation. And then he went on to explicitly say that in software engineering, those documents must be different from source code. And that, I think, is a misunderstanding which is arbitrary and harmful. In the same way that programmers are suspicious about the accuracy of comments and prose documents about their systems, Eugene Ferguson, in his book Engineering in the Mind's Eye, says this about engineering documents. Although the drawings appear to be exact and unequivocal, their precision conceals many informal choices, inarticulate judgments, acts of intuition, and assumptions about the way the world works. We're going to come back to the notion of engineers designing by documents a little later. Number 5, engineers use mathematics to prove designs correct. This is a widely held opinion, and it's one of the reasons people say that software development is not real engineering, because we don't have math to prove the things that we think we know about our systems. I know in Australia you didn't have the newspaper comic strip culture that we have in the United States. But I think most of you are probably familiar with Calvin and Hobbes. As a father, I have tried to model myself on Calvin's dad in my relationships with my children, which means that when they ask me things about how the world works, I invent ludicrous explanations and tell them to them and see how this goes. And so here's an example. Traveling on vacation with his family, Calvin sees a sign and says, "How do they know the load limit on bridges, Dad?" And Calvin's dad confidently and enthusiastically says, "Well, they drive bigger and bigger trucks over the bridge until it breaks. Then they weigh the last truck and rebuild the bridge." And, that's just the way it works in our family. Why is this funny? Why is that cartoon funny? What are we laughing at? It's not true. In fact, it goes beyond just not true. It's absurd. Nobody would ever do something so stupid. How many of you have seen the video of Boeing engineers winching up the wings on a 777 prototype until they break? I encourage you to find it on YouTube. It's easy to Google for. I encourage you to watch it for 2 reasons. One, it'll make you feel really safe flying in a 777 because, wow, those things bend a long way before they break. But the other reason, it's a full-sized plane. The interior, the fuselage isn't complete and everything, but the wings are, just the way they would be on a completed plane. And they attach cables to the wing tips and stick them on a winch up on the girders on the ceiling and crank them up until they break explosively. And when that happens, the engineers watching get all excited in kind of a nerdy engineer way, Cool. Why do you think they get excited? They learned something. What do you think they learned? That's right. They got excited because the wings broke at exactly the angle that they predicted. And what that means is that the test proved their math correct, not the other way around, right? And it turns out, if you look at the history of engineering, mathematical models were introduced as a cost-saving measure. Those of you who have an engineering background, what is the most common prevailing strategy that engineers use to ensure the robustness of systems after they enter the real world? Many trials. Testing and verification. Safety factor. Over-engineering, right? And if you're a civil engineer, over-engineering means adding more material. And if you're a civil engineer, material is the dominating cost of your project by an enormous margin. So if you can come up with a mathematical model that can give you some confidence about what's actually needed, then you can reduce the amount by which you have to over-engineer and save a lot of money, and maybe win a contract over your competitor that you wouldn't win otherwise. None of this is to say that math can't prove something correct. And you'll hear in Kathleen Fisher's keynote tomorrow some really interesting stuff about that in the realm of software. But the idea that it can't be engineering unless you've used equations to prove your design correct is false. Number 6, engineering design requires modeling. And this is another one that's true but has been misapplied in software engineering. In particular, we should remember that models can take many different forms and that they are never 100% accurate. There's a famous quote by George Box that applies here: all models are wrong, but some are useful. I'm going to tell you 3 stories of models. In Switzerland, in the early part of the 20th century, there was a civil engineer named Robert Maillart. And during the time when Maillart was working, there was this new material that was being used called reinforced concrete. And it was already being used in building bridges, but it was being used as kind of a cheaper stone. So the designs that were being built were just like the older stone bridge designs, except in place of stone, they used reinforced concrete. And Maillart realized that reinforced concrete was a very different material with different properties and could be used to build different kinds of bridge designs that wouldn't work with stone. And he made his name building beautiful, graceful, lightweight, and inexpensive bridges like the Waldschilbach, which is one of his most famous, out of reinforced concrete. He was very harshly treated by the civil engineering establishment in Switzerland and Europe at the time, and was called a charlatan and a thief. It was said that he was stealing from his customers and endangering lives by building bridges that would fall down. And the reason is because he did not have mathematical models sophisticated enough to really demonstrate conclusively that these bridge designs were sound. And I say this, on the heels of the previous comment about math, just to show that software development is not the only field that's kind of lost the plot occasionally about what math, the role of formal methods in engineering. But, he ended up building a lot of bridges, and the only one that fell down in an avalanche, which, okay. How do you think he slept at night? Well, we've kind of heard answers to this already, empirical testing and verification. He designed his bridges with an intuitive understanding of the physics involved and how forces were distributed through the structure. But he also built models of different scales, and in his workshop he had barrels full of rocks that he would roll over the models and invite friends over to jump up and down on them and things like that, and convinced himself that the designs were sound. And because they were so inexpensive, numerous small rural communities in the mountains of Switzerland were able to afford to build a bridge to serve their community that they would not have otherwise been able to build. Maillart had a contemporary, a Hungarian named Leon Moisseiff. Moisseiff went to the United States and was a consulting engineer on a number of large suspension bridge projects, including several around the island of Manhattan, the Mackinac Bridge in Michigan, and the Golden Gate Bridge in San Francisco. And during this work, he developed the best and most reliable and accurate mathematical model of suspension bridges that anyone had ever come up with, and he called it deflection theory. And it was used in various degrees of refinement on those bridge projects. And finally, Moisseiff got his own bridge project where he was the principal engineer and got to show what deflection theory could do if taken to its limit. And he built the Tacoma Narrows Bridge. Now, if you read books about why this happened, you'll learn that like the immediate cause was that the deck started oscillating, and due to its length and width and thinness, it started oscillating at the resonant frequency, and it amplified it, and it tore itself apart in a like 39 mile per hour wind or something like that. But why did it start oscillating in the first place? And it turns out the reason for that is that deflection theory was tragically incomplete. It took into account gravitational stresses, downward stresses from the load of the bridge weight itself and from vehicles driving over it. It took into account sideward stress from wind. But what it failed to account for, because nobody had ever seen the phenomenon before, was that if you build a suspension bridge deck sufficiently thin relative to its length, it can act as an airfoil and generate lift. And it did not account for that upward stress from lift as wind blew across the bridge, and that started the oscillation process that led to the bridge's demise. I've quoted from Eugene Ferguson before. I'll do that again. Structural analyses, indeed any engineering calculations, must be employed with caution and judgment because mathematical models are always less complex than actual structures, processes, or machines. And I'm running a little bit behind, so I'll skip over this third story very quickly. The Cathedral Sagrada Familia in Barcelona by the Catalan architect Antoni Gaudí is very unusual on the interior, and it also employs shapes and structures that he did not have sufficient mathematical sophistication to really analyze carefully. And so what he did was he exploited an old engineering principle called the catenary principle in a fascinating way. And if you look in the basement of this, the museum in the basement, you can see the models that he built. He would build these inverted hanging string models where strings represented the columns and walls and support structures, and he would hang little bags of sand from them to imitate, different gravitational forces on the parts that were intended to support heavy loads, and use this to determine the proper shape for these columns and vaults. And this is from a smaller church that he did as a study for Sagrada Familia, and they would lay muslin inside the model to give better form to it, and then take pictures of that model and turn them upside down so they could see what it would look like, and stick cameras inside and see what it would look like on the interior. And they never built a full-size string model for Sagrada Familia, but they did small-scale ones for certain parts of the structure to figure out what those columns should look like and how they would be safe. And eventually built some plaster models. And recently architects have used sophisticated math and computer analysis to verify that the designs were sound, even though they were done in a very empirical kind of way. So, misleading or false assumptions about engineering that led us astray. Engineering is defined in predictable. I won't read all those. That's just for a summary in the slides. So that led us to a point where we had a false foundation to build engineering on. And the false foundation kind of looks like this. And this is based on the work of Jack Reeves, who wrote a fascinating paper in the early 90s called What is Software Design? The software engineering in those days, those classical methods of software engineering, was based on an analogy with traditional engineering disciplines, and the analogy went something like this. You would have an engineer in those old methods that would produce a design and then hand that design off to laborers who would build the finished product. And so the thinking apparently went, if that's the way traditional engineering disciplines worked, then for software engineering, we should have engineers build a design and hand it off to laborers so that they can build the finished product. Where did this fall down? Come on, you've all experienced it. What? Outsourcing to India. No. The biggest problem was that we never figured out a way to express a software design so that coders, the laborers, could accurately build what the engineers intended, right? We never figured out a way to make it precise enough to have any confidence that it was correct or complete. And so the result was that programmers in this division of labor would end up having to redesign or design stuff to fill in the gaps and make it work when, in theory, that was supposed to be the engineer's job at the front end. And interestingly, the fact that this model can't work was known in 1968 at the Garmisch NATO Software Engineering Conference. Peter Nauer, on that occasion, said, "There is no essential difference between design and production, since even the production will include decisions which will influence the performance of the software system and thus properly belong in the design phase." And Doug Ross said, "The most deadly thing in software is the concept, which almost universally seems to be followed, that you are going to specify what you are going to do and then do it. And that is where most of our troubles come from." So let's revisit this. If we can't figure out how to express a software design on paper so that programmers can reliably produce it, maybe we should just train those programmers in design and engineering and let them be the software engineers. And another problem with this analogy is that files full of source code isn't what people pay for. They're paying for deployed systems working on machines. And in fact, Jack Reeves said that source code is actually the design document. Okay. If the source code is the detailed design document, and nobody here is saying that we shouldn't also have higher level diagrams or overview design documents that lead us into that, but if the code is the detailed design document, what corresponds to the laborers building the finished product up on the top row? Compilers and language implementations. And the finished product, of course, is deployed software running on machines. Now, before we go away from this, I want to point out one other thing. What's the most expensive part on the top row? Materials and labor, building the thing. Step 3. What's the most expensive part on the bottom row? Design. And in fact, we have this enormous luxury in our field that once we have put a design on paper, by which we mean in a file in the computer, we can build it effectively instantaneously and for no cost and completely reproducibly with perfect fidelity to our design every time. And we spend a lot of time in software trying to figure out how to not write source code until we really knew what we needed. But in actual fact, that upside down cost model between traditional engineering disciplines that work with materials and software development means that we should do it a different way. Ask your friendly neighborhood aerospace engineer how much formal analysis and modeling she would do if building a prototype of the design and testing it were effectively instantaneous and free? And the answer is probably none at all, but it's sure a lot less than it would be if they have to carve the model out of clay or whatever like that and stick it in a wind tunnel. And in fact, we're getting so good at modeling structures and fluid dynamics and things like that in computers now that even older engineering disciplines like civil engineering are being transformed to do much of their design and validation work through trial and experiment in computer simulations rather than the older school mathematical methods. What's my stop time? 6 minutes. I better hurry. Software, we talked about the flawed assumptions of engineering. Let's look at what software is really like, and I'll go through this quickly. Because of that inverted cost model and the characteristics of our field and our tools, software development should be empirical, iterative, and experimental. And I'll skip over the details, but I wrote a paper a few years back in 2005 analyzing extreme programming and finding the underlying structure behind it and showing how it is actually a very rigorous, disciplined process that subjects all design decisions to a gauntlet of feedback loops that can catch them. And I describe XP and other agile processes applied this way as economically optimized feedback engines that gets feedback on every decision as rapidly as it is economically feasible to do so. So if it's a decision that's very easy to validate, you get feedback on that very, very quickly. If it's a kind of decision that's very costly to validate, you do that more slowly, but it's arranged in that more or less optimal way. Applying computer science is at most half the challenge of software development. Really, the challenges are at least as much in communication and coordination of effort and how to divide effort and parcel it out and things like that. Most engineering disciplines try to build things that are stable and rigid, but in software development, we need to learn how to make things that are easy to change. We need to focus on that. And finally, our source code is our document, it's our math, and unlike, the math that other disciplines have, our math can do stuff for us. We have documents and mathematical analyses in our source code that can be used to self-validate and tell us if our design matches the specification for us. Our programs are also our models. So if we want to define a better future for software engineering, first, let's admit to ourselves and to everybody watching us that what we had in the 80s was not a good model for software engineering. Second, we need to establish an inclusive definition of what software engineering is. Most of the definitions that I've seen have taken the form of it's engineering if you do it this way. But we don't know yet for sure the best ways, so we need to have an inclusive definition, and I will show you the one that I propose. The best definition of any kind of engineering discipline I've ever seen is this one from the Structural Engineers Association. Structural engineering is the science and art of designing and making with economy and elegance structures so that they can safely resist the forces to which they may be subjected. And so, just as a starting point, I propose this definition of software engineering. It's the science and art of designing and making with economy and elegance systems so that they can readily adapt to the situations to which they may be subjected. Third, pursue a research agenda focused on the real problems. We should embrace code as a design document, formal specification, and modeling tool. Understand and leverage the feedback loops in our processes and our tools. Really exploit that inverted cost model where the things that other engineering disciplines have to struggle with and that are the most expensive things are effectively free to us. Understand and build on how programmers think about programs, which we've neglected woefully in our software research and also in our development of tools. Develop tools that help us navigate the multiple dimensions of software. Software internals are multidimensional. I think the number of dimensions is much greater than 3, and it's almost certainly not an integer. And so tools that lock us into a 2-dimensional view of our programs hinder thought, they don't help it. Attack the iterative design dilemma, where depending on how much you care about the design and refactor as you go, iteration is either the best or worst way to build a good system. It all hinges on that attention to design. And for now, avoid prescriptions about how you must do it to be called engineering. Thank you very much.